Okie dokie, welcome back. Moving on to the next stop point. Solve problems, create models, and make quantitative predictions by applying the equations of motion relationships for uniformly accelerated and constant rectilinear motion. So what's this stop point all about? So we can see there's the three things that's covered here: solve problems, create models, and make quantitative predictions. What do we need to do that with respect to? Well, by applying the equations of motion relationships for uniformly accelerated and constant rectilinear motion. This last sentence here is basically the equations that we've derived in the previous stop point for projectile motion. So in other words, we're going to be using the equations that we've talked about previously in order to solve generally problems, create models, and make quantitative predictions. There are two main types of problems in projectile motion questions. The first one is when the projectile starts and ends at the same height. So you have that as the first example there. It starts and ends at ground level. Now, because we're talking about uniformly accelerated motion, we can split up the motion of the projectile into a y component and an x component, or in other words, a component which acts in the same direction as the constant force we're talking about, gravity g, and a direction in which this force does not act at all. In fact, no force acts in this direction. So in other words, x is always equal to 0, and we define a y is equal to g, right? Because it's acting in the opposite direction to what we define y direction to be, we usually say minus 9.8. The second type of question is where the projectile starts at a different level to where it ends up. So in this case, the projectile starts higher up, maybe on a cliff, for example, shot up, comes back down. As before, the path is parabolic in nature, and the components can again be split up, but because of the nature of the question, we have to apply slightly different assumptions when answering them. Let's concentrate first on the first type, so where the projectile starts and ends at the same height. Now, as we're saying, the equations of motion are these that we described previously. These equations are only applied in the x or y direction independently, right? So you always need to specify in which direction you are applying them. Now, how do we solve a problem in projectile motion in general? Well, first we draw a diagram of the situation. What information do you have at the start, given and implied? Implied means that there is assumptions that you can make based on the scenario that you're given. Because the projectile starts and ends at the same height, one thing that we can straight away say is that the time taken for the projectile to reach its maximum height, let's call this time Tm, where it reaches its maximum height, Hm, is always actually going to be half of the total time. So time taken for the projectile to reach its final resting point is going to equal to Tm times 2. What information does question problem asking for? So in other words, it could be a number of things. For example, it could ask for what is the maximum height. It could ask for the time of flight, for example. It could ask for the range, how far away in the x direction does the projectile reach. These are all possible questions. The next point is to link what you have with what you need via the equations of motion. Once you have values for certain things, so for example, you might have ux, you might have uy, the initial starting velocity in the x and y direction, or even just u together with an angle. These are all starting points, but you need to link it via the equations of motion. So you will link this to whatever you are looking. And at the end, once you have that link, it's a matter of solving the equation. So here we just have a number of examples of possible variables that are either given or asked for. So examples here are hm being the maximum height, tf the time of flight, r the range in the x direction, u the initial velocity, ux the initial velocity in the x direction, uy the initial y velocity, and theta the angle of the projectile. So any of these could be given and any of these could be asked for in a projectile motion question. Okay, so now moving on to the situation where the projectiles start and end at different heights. How will our problem solving change? Well, the steps should remain the same, right? You're still going to be drawing a diagram of the situation, looking at the info that's given at the start, and what's given and implied. So the thing that will differ here is what is implied from the situation. What infers the question asking for, again, would be one of the ones that we've discussed before. Link what you have done with what you need via the equations and then solve. So in an example here, if we have the projectile starting on the top of a column and it's shot up into the air, it'll eventually come back down, but land at a point lower than where it started. Because the projectile ends at a point lower than where it started, we no longer have the situation that the total displacement in y direction is equal to 0. Right? That's no longer true. In this case, if this is our 0 displacement in the y direction, it actually ends up going in negative, right? So for this situation, Sy is actually less than 0. Another aspect is that the total flight time is no longer equal just the 2 times the time taken to reach maximum height. Time taken to reach maximum height here is going to be different for the time taken to reach end height. Right? These two are no longer equal, therefore we can no longer just easily multiply by 2. What will remain the same though, of course, is that things can also be split up into the x and y components. All the other things will remain the same, right? If you want to find the maximum height, you're still going to be looking for the point in the path where Vy is equal to 0. That'll give you this point right here, right? There are other things that stay the same, but these are some of the differences. 2 other possible scenarios for projectiles starting and ending at different heights is a projectile launched purely in a horizontal direction, so there's only a horizontal component. So in this case, ux is some positive number and uy is equal to 0, right? Because there's no y component initially. Another situation is where the projectile starts at a lower height and ends at a higher height. In this case, you're going to have both a y and an x component to your initial velocity. And as was the case with the projectile starting and ending at the same level, we have a number of different variables that can be asked for or given in the question. So you could have the time of flight, for example, the maximum height, the range from the start to the end, and of course the initial velocity and the angle, as well as the broken down components of uy and ux. And this is where we'll leave this video. Basically, this was an explanation of different ways that questions can be asked in this Dotpoint and strategies for answering these types of questions. In the next video, linked to this Dotpoint, we will go through a number of examples showing both cases where you have a projectile starting and ending at the same height, and the case where the projectile starts and ends at different heights. Thanks for watching and see you in the next one.